Hi, I'm Sven. One more thing about solvers. There are so many possible decisions and we need to check them all to find the best, right? Well, no. It's the magic of solvers that we can find our optimum incredibly fast. So today, let's have a look into those black boxes and see how they work. Welcome to Optano. In optimization, a decision is a specific value of a variable. Of course, decision variables cannot take every possible value. Instead, they are constrained by the knowledge that we have about the problem we want to solve. For example, if we model a supply chain network, then there's a maximum transportation capacity between some locations based on the number of trucks, which is a constraint. We can think about this visually. A constraint is a boundary where the variable values that we allow for are on the one side and the values that violate the constraints are on the other side. A typical model has lots of constraints and they enclose a space of acceptable solutions. In 3 dimensions, this would be a kind of distorted ball shape, but there are still way too many valid solutions inside this shape. And this is where the solvers kick in. Solvers exploit the mathematical properties of this shape and combine them with clever search strategies. An algorithm you might have heard about is called simplex. Visually speaking, it does not care about the inside of our solution space. This is because our optimal solution is always a maximum or minimum. And this means it's kind of pushing into the boundaries of the solution space. Now, simplex makes use of this. It travels on the outside, checking the corners where some constraints meet. And from such a corner, it travels along the edges to the next one, and to the next, and to the next, until a corner with an optimal solution is found. So it's quite a bully and corners the optimal solution on the far edge of the constraints. Mathematically, these corners are typically real numbers, so we are fine for linear problems. However, it does not work if we look for integers or binary decisions. But simplex may help if we bring in support, like the cutting plane algorithm. First of all, imagine our solution space, and we look for integer solutions now, not real numbers. Then we expand it and allow for real-valued solutions, not only integers. We kind of blow it up a bit. But now we padded everything with real values on the outside, which means we can apply simplex now to find an optimum at a corner, as before. But probably the optimum is not integer anymore, because we expanded our problem to a linear one. Now we find and add a constraint that separates the real-valued solution from the actual solution space of our mixed integer problem, which is smaller to begin with. And this constraint is called a cut, and finding it is part of the magic. So overall, we expand our mixed integer solution space to a real-valued solution space and then start to cut away what we added, cut by cut. And this way, we repeatedly solve simple problems, peeling away layer by layer until we create a space where the optimal solution of the problem is indeed an integer. There are more algorithms to refine this, like branch and bound, branch and cut, branch, and a lot of other topics. You get the gist. We like to treat solvers as magical black boxes, but it's worth to understand their basic principle. They split the search space into smaller chunks one way or the other and only search the corners of it where an optimal solution could hide and ignore the rest. And this is why solvers are so efficient. See you next time and stay safe!